Section 1.4, Multidimensional Kinematics. In the last few videos, we've been building up intuition about some of the mathematical tools that we need to describe the world we live in. We want to consider now the two-dimensional case, whereas in the second video we considered the one-dimensional case. We're now allowed to consider multi-dimensions thanks to vectors, which we learned in the last video. We now want to consider the observer situation that we had in the one-dimensional kinematics example, but now in 2 dimensions. The position will be modeled by a vector function, r of t, from an observer. So we have an observer O, and then we have a trajectory drawn by our particle, and this will be modeled by r of t, which will be changing based on where the particle is in relation to the observer. In addition, we will take the time to make a coordinate system such that we have a pair of basis vectors, which will be e hat sub x and e hat sub y, which allows us to decompose r of t into x of t and into y of t. Thus, we can make the following decomposition. Additionally, we can use the column vector notation to have x of t and y of t to build our column vector. If we want to find the magnitude of r of t, we can take the Pythagorean theorem and add x squared plus y squared and take its square root. We can additionally decompose r of t if we know the angle as well as the magnitude. Now the magnitude and the angle will be changing with respect to time, so they will be functions of time as well. Thus we can define r of t as being equal to r of t magnitude r of t, and this will be a function because the magnitude will change in terms of the cosine of theta of t. And then for the y component, we will have r of t times the sine of theta of t. From this, we can define a bunch of quantities, the first of which will be the average velocity. To get the average velocity vector, we will take the change in r over the change in t, which will be rf minus r initial over final time minus initial time. Taking the limit will give us the expression for the instantaneous velocity vector, v equals r dot. Of course, this is the same as x dot of t and y dot of t. To find the average acceleration, we do a similar process except with the velocity. So we take the final velocity minus the initial velocity over the final time minus the initial time. This gives us now an expression in the limiting case for the instantaneous velocity, or the instantaneous acceleration. A vector is equal to the first derivative of v vector, which is equal to the second derivative, or we're not using x anymore, but r, second derivative of r vector, r double dot. Essentially, we recover the same relationship that we had in 1 dimensions, but we are now dealing with vectors. Again, we have now adopted the notation such that dx dt is equal to x dot. If we are not taking the derivative with respect to time, we will make that clear by using Leibniz notation. But when it is a time derivative, we will use x dot. Using the vector notation, we can find the following relationships such that we have r of t is equal to x of t and y of t. V of t will be equal to x dot of t, y dot of t, because we can take these components y's. This will be equal to v sub x of t, v sub y of t. Finally, for acceleration, we will get the following relationship that we have the derivative of vx of t and the derivative of vy of t, which is equal to a sub x of t, a sub y of t. Let's try an example. Let's say that r of t equals 4 plus 2t for the x component, 3 plus 5t plus 4t squared for the y component, and 2 minus 2t minus 3t squared for the z component. For the velocity, we will differentiate this using the power rule by component. For this, we will get 2 for the x component, 5 plus 8t for the y component, and negative 2 minus 6t for the z component. Finally, for acceleration, we will get 0 for the x component, 8 for the y component, and negative 6 for the z component. Say I wanted to ask for the magnitude of the acceleration vector, we would get a is equal to the square root of 8 squared plus negative 6 squared, which is equal to 10. Finally, if I wanted to find the angle of this with respect to the x-axis, I would find the argument of said vector. The argument of the acceleration vector is equal to the inverse tangent of y over x, or y over z, or z over y, which is equal to negative 6 over 8. It's very important that we specify which axis we are finding the angle with respect to, because in this case we do not have an x value that is 0, and that was not imported into our calculation for the magnitude either. So we need to be sure that we're looking at that. Finally, one more important thing, at least dealing with vectors here in 2 dimensions or more dimensions, is that say I want to find the unit vector. If I want to find a basis vector, I can take the magnitude, or I can take the vector and divide it by its magnitude, and I will get a basis vector. That's a small definition for us right there. I would now like to take the time to integrate the equations of motion for our multidimensional kinematics. We will start with a dual component acceleration such that our acceleration vector is equal to a sub x and a sub y. This will be with constant acceleration. We should note that acceleration is equal to the first derivative of velocity, so we can use the method of separation of variables to solve the differential equation such that we get the integral between we get the integral between v naught and v of dv is equal to the integral between t naught and t of a dt. Now we will get the expression that v minus v naught is equal to a times the integral between t naught and t dt. Thus, we get the equation v minus v naught is equal to the acceleration vector times t minus t naught. Again, these are simple applications of the fundamental theorem of calculus. To go from velocity to position, we get v is the first derivative of the position function. And so we can use a very similar method. We get the integral between r naught and r of dr is equal to the integral between t naught and t of v dt. Thus, we get an expression very similar to what we had for one-dimensional kinematics, that our position function is equal to r naught plus v naught times t minus t naught plus 1/2 acceleration t minus t naught squared. We can break this down into components with a matrix equation. Thus, we get x of t, y of t is equal to x naught, y naught plus v naught x, v naught y, t minus t naught plus 1/2 a x, a y, t minus t naught squared. Thus, we get the equations of motion for constant acceleration. Here we have it for velocity, and here we have it for position. Here we have it in both components. So that would be a big definition for all of them. Now, for working in even more dimensions, you can expand this. Imagine these matrices go x, y, and then they keep on going down, and you will get the same kind of thing, x naught, y naught, z naught, w naught, whatever you have, plus v naught x, v naught y, and you keep going, t minus t naught, plus 1/2 ax, ay, keep on going, t minus t naught squared. So you can see the expandability that the vectors allow us in this scenario. Finally, I would like to discuss particle motion and looking at the equations of motion for particle motion through the context of an example. In particle motion, we will consider a scenario where we have a parabolic trajectory. That's how that works in this kinematics world. So we will have a y-axis and an x-axis. Note this is no longer x and t. We have x and y, and we have vector functions now. So we will be launched with some initial velocity. We shall call that the initial velocity v naught, or we shall call the magnitude v naught, which can be divided into v naught cos theta and v naught sine theta, given that theta is the angle that we launch with. Likewise, we will get a parabolic trajectory, and this will include some maximum y height, which I shall call y max. It will include a range, which we shall call x max. And we will also have, again, that elevation angle of theta.